So in the previous video, we saw how we should define the average value for an integrable function. And so f is an integrable function defined on the interval a, b with values in the real numbers. Then we define its average value in this way. F ABE, the average value of f, equals 1 over b minus a times the integral from a to b f of x dx. Now in this video I want to discuss an important theorem about average values. And that theorem, which I've written here on the board, is called the mean value theorem for integrals. And it says the following. If f is a continuous function of AB, then there is a point P in AB such that f of P is equal to the average value of f. And so this says that a continuous function always assumes its average value at some point in its domain. Right. Now, why is this true? Let's look at a few pictures to help us see why it is true. Right. So this isn't a complete proof, but it will help you to understand the proof. Right. So we remember f is continuous. And a continuous function on a closed bounded interval AB always assumes a minimum and a maximum value. Right. So if we draw a graph, there's A, there's B, y equals f of x. Right, so we see here at this point C, f has a minimum value, right? Say f of C equals small m, and here at this point, let's call that D. F has a maximum value. Let's call it big M is f of B. Okay. So we see that small m is always less than or equal to f of x less than equal to big X. And that's for all x in AB. Okay. So from that inequality, it now follows that if we integrate f, we get the following. Right? We're going to get small m b minus a less than equal integral a to b. Let me just write it over there. F of x dx less than equal to big M b minus a. Right. So, we can see that this MB minus A, right, that's going to be a rectangle, an area of a rectangle, sits there, right? And this other term, big MB minus A, that's also going to be the area of a rectangle. Right, that's going to be area of this whole big rectangle. Okay. So the yellow area gives you that term, and the sort of brownish area gives you that term. Right. So that it's clear that the integral from a to b of this f of x dx should be between these two areas. Right? Because that area, right, that integral is just the area under the curve. Right, so basically the purple. Okay. And this is not a proof of that fact, it's just a sort of pictorial indication of why it's true. Right? So now, if we divide throughout these two inequalities by b minus a. Right? So we're going to divide that out, and we end up with 1 over b minus a. We divide that out. Right, so what we have here in the middle, then that's just the average value of f. So we have f of c, which is small m, less than equal the average value of f, less than equal to big M, which is f of d. Right. So what we see from this inequality is that the average value of f sits between f of c and f of d. Right, so there's f of c, there's f of d. So the average value sits, say somewhere here. Right. And now again, because our function f is continuous, right, the mean value theorem tells us, not the mean value theorem, the intermediary value theorem tells us that at some point between c and d, right, f must assume this value. Right, and you can again see that from the graph. Right, if you draw the line y equals f, average value of f, then eventually it will intersect the graph y equals f of x. Right. Right, so we see at this point p, f has to equal its average value. Right. So the intermediary value theorem now tells us that f of p is equal to the average value of f for some p between a and b. Right. So you see the proof is actually quite simple. Right? All we have to do is to realize that because f is continuous, it has a minimum and a maximum. Right? And then this inequality falls out just by integrating and dividing by b minus a. Right? And then it's just a matter of applying the intermediary value theorem. Alright. So this theorem, well, it's interesting in its own right, because it tells us something about how continuous functions relate to their average values. But it's also a very important tool, right? Because it allows us to apply things we know about integrals to the values of the functions. Right? And we'll see shortly a very, very interesting and important application of this result.